Hello students. In this session, we will take up S block elements. Okay, the topic S block elements in inorganic chemistry. And using a question, we will focus on the following concepts: solubility, basic strength, and thermal stability of groups 1 and 2 compounds. So here is the question. So four comparisons have been given with respect to four properties: basic strength of oxides, solubility of sulfates, thermal stability of carbonates, and melting point. Amongst these, which one of them is not correctly matched? There could be one or more than one. Okay, so let's understand each of these properties, after which we will identify which amongst these comparisons is correct or wrong. Okay, let's first focus on the basic strength of oxides. Basic strength of oxides, and these are group 1 metal oxides. Okay, so that is the first comparison. All right. Now, any group 1 metal oxide will dissolve in water to produce an alkaline solution. So an alkaline solution is what is expected when a group 1 metal oxide dissolves in water. Okay. So what are the various group 1 oxides? You have lithium oxide, and then you have sodium oxide, potassium oxide, rubidium oxide, and cesium oxide. Okay. Now the reaction, the ionic equation is this: the O2 minus from the metal oxide, okay, the O2 minus from the metal oxide interacts with water to produce 2OH minus aqueous. In other words, whichever metal oxide can easily release the O2 minus from the oxide is the one which will most readily dissolve in water to form an alkaline solution. All right, so that is what we have to find out: which amongst these group 1 metal oxides undergo easy decomposition. We know that the size of lithium ion is the smallest, and the size of cesium ion is the largest. So cesium ion, being the largest, is referred to as the most electropositive, most number of shells, and therefore can easily lose one electron. Most electropositive, whereas lithium ion will be the least electropositive. Now, because of the smallest size, okay, we can apply Fajan's rule here. So you have lithium ion, and we have oxide ion, correct? The oxide ion has got two shells. The oxide ion has got two shells. So this is the electron cloud of the oxide ion. Let me denote the electrons in the oxide ion. You have got two electrons in the first shell: 1, 2, 3, 4, 5, 6, 7, 8. Now, because of the small size of lithium ion, they will easily attract the electron cloud towards themselves. The extent of polarization is high. Okay, the oxide ion in lithium oxide is highly polarized. Because of the high polarization, it is very difficult to break the lithium oxide bond, and therefore the oxide ion is not easily released by lithium oxide. We look at the other extreme, cesium oxide. Because of the largest size of cesium ion, the cesium oxygen bond can be easily broken, and the oxide ion can interact with water to produce an alkaline solution most readily. So high concentration of OH minus ions is produced when cesium oxide dissolves in water. So what is the correct order of the basic strength of metal oxides, of group 1 metal oxides? Lithium oxide is the least basic, followed by sodium oxide, followed by potassium oxide, followed by rubidium and cesium oxides. Okay, this is the correct order of basic strength of oxides, and let's see what is given. The exact reverse order has been given, and therefore this is incorrectly matched. Okay, the basic strength of oxides and the order do not match. All right, now let's move on to the solubility of sulfates. So our next discussion is on solubility of sulfates. And here we have the group 2 metal sulfates, right? The group 2 metal sulfates, which means MSO4, right? So solubility, metal sulfate dissolving in large excess of water to form metal sulfate aqueous. Now, this dissolution or the solution enthalpy depends upon two important enthalpies, which is lattice enthalpy and the other is the hydration enthalpy, right? So the solubility depends upon lattice enthalpy and hydration enthalpy. Why lattice enthalpy? First, the ionic compound has been should be split into gaseous ions. That is lattice enthalpy. And once the gaseous ions are formed, they will interact with water to produce. So each ion, the positive ion and the negative ion, will be separately surrounded by the solvent molecules. Here the water molecules, right? And hydration enthalpy is the next important feature. All right. And if a large amount of energy is released, we say that solubility is high in that particular solvent, here water. All right. So two important factors determine the extent of solubility of of an ionic compound in water or a polar solvent. Here the ionic compound is metal sulfate, and we're talking about group 2 metal sulfates. So let's first make a note of the various group 2 metal cations. We have beryllium ion, right? And this is sulfate ion. And then we have magnesium ion, calcium ion, strontium ion, and barium ion. In all these cases, the anion, the negative ion, is the large sulfate ion, right? Large sulfate ion. Okay, first let's deal with the hydration enthalpy. Smaller the size of the cation, greater the interaction with the solvent or water molecules, more exothermic the interaction is, higher the hydration enthalpy. But as we move from beryllium ion to barium ion, the size increases, right? And when the size increases significantly, the delta H naught hydration of the metal cation will also decrease, right? As the size increases, weaker interaction with the surrounding water molecules, lesser amount of energy released, or more endothermic, and therefore the hydration enthalpy will decrease significantly. Okay, so there is a significant decrease in hydration enthalpy. Now, what about the other component, lattice enthalpy? Lattice enthalpy involves the electrostatic force of attraction between the positive ion and the negative ion, right? As we move from that, so that also depends upon the size. So as the size increases from beryllium ion to barium ion, here also the lattice enthalpy will decrease. Lattice enthalpy will also decrease, but less significantly because the sulfate ion is large. So decrease in lattice enthalpy is less, whereas the decrease in hydration enthalpy is more. And therefore, the overall result is what? Solubility decreases. Solubility decreases from beryllium sulfate to barium sulfate. All right. So let's see what is the order given here. So barium sulfate is the least soluble, whereas beryllium sulfate is the most soluble, and that is what we deduced. So second comparison is correct. Now let's move on to thermal stability of carbonates. Okay. So let's understand what are the determining factors. Now, thermal stability again depends upon how readily the compound or the ionic compound decomposes when temperature is increased. Okay, so now we have the group 2 group 1 metal carbonates. We have lithium carbonate, and then we have sodium carbonate, potassium carbonate, rubidium carbonate, and cesium carbonate. Correct? Amongst these carbonates, lithium carbonate, now lithium ion is the smallest. So here again it depends upon the size, right? Depends upon the size. We have lithium ion here. This is the smallest. Because of the small size of the lithium ion, what can happen? There is a significantly high covalent character in lithium carbonate. Why? So here let's represent the lithium ion and the large anion carbonate ion, O minus, C double bond O and O minus. Okay, let me draw it with respect to the trigonal planar shape. So O minus, C double bond O and O minus. Now because of the small size of the lithium ion, it will attract or pull the electron cloud of the oxide ion towards itself, forcing the breaking of this bond, resulting in the formation of lithium oxide and carbon dioxide. So we need two lithium ions here. So the carbonate ion is easily broken down. And so in other words, the lithium carbonate is easily broken down to lithium oxide and carbon dioxide at very low decomposition temperatures. The temperature at which lithium carbonate decomposes is very low. Low decomposition temperature, that signifies low thermal stability. Low thermal stability. Thermal stability is a stability on heating. It is unstable towards heat. On the other hand, every other carbonate, as the size increases, the extent of polarization will decrease. And from sodium carbonate to cesium carbonate, they are thermally stable and they have high decomposition temperatures. And obviously, the decomposition temperature will increase from sodium carbonate to cesium carbonate. Cesium carbonate will have the highest decomposition temperature because of the least extent of polarization of the large carbonate anion. So what is the order of stability? Lithium carbonate is the least stable and cesium carbonate is the most stable. Is that the order given? Yes, that is the order given, and therefore that is also a correct representation. And now moving on to the last property, melting point. Now, melting point also depends upon thermal stability, which in turn depends upon the extent of polarization. The cation is fixed. So we have sodium fluoride, sodium chloride, sodium bromide, and sodium iodide. Sodium ion is fixed, but you notice that the anion, the size of the fluoride ion is the smallest. Whereas as we move from fluoride ion to iodide ion, the size of the anion increases for the same fixed small cation. So because of the largest size of the iodide ion, there is the greatest extent of polarization. Greatest extent of polarization in sodium iodide. The sodium ion will strongly pull the electron cloud of the large iodide ion, and that results in most significant covalent character. Most significant covalent character in sodium iodide. Most significant covalent character in sodium iodide, and therefore sodium iodide should have the least melting point. Okay, sodium iodide should have the least melting point. Melting point is high for ionic compounds and fluoride ion being the smallest will be the most ionic. Sodium fluoride will be the most ionic, and being most ionic, it will have the highest melting point. Okay, so the least one would be sodium iodide, and the highest melting point will be for sodium fluoride. Let's see how the comparison, how the order is written. It's an incorrect order, right? Sodium iodide has the least melting point, while sodium fluoride has the highest melting point. Okay, so amongst the four properties, the properties 1 and 4 were incorrectly matched, correct? And 2 and 3 were correctly matched. So by discussing this question, I hope you have been able to recollect these important properties of S block elements, namely basic strength, solubility, thermal stability, and melting point. Thank you.